Okay, let's get started. Good afternoon, everyone. I'm Rick Fienberg, AAS Press Officer, and I'm extremely excited to welcome you to this press conference because it is the 10th and last press conference of a very busy and very tiring week. But it's been a really good week, too. We're glad you're here with us. The topic of this press conference is Evolving Stars and Nebulae 2, because we've already had a whole briefing devoted to evolving stars and nebulae. This is, of course, coming to you live from the 237th virtual AAS meeting, which is being held anywhere and everywhere. I don't think there's any two of us in on the screen today that are in the same state even. Let me introduce you to my staff here today. Joining us from AAS Nova, which is our website where we highlight interesting and potentially newsworthy articles that are appearing in our journals, is Susanna Kohler. She's the editor of our AAS Nova website. AAS Media Fellow Tharani Konchadi is a graduate student at Texas A&M, and she will be monitoring the Slack channel during the briefing. And Haley Wall, a graduate student at West Virginia University, has spent the meeting as the Astrobytes media intern. She's been learning how the press operation works behind the scenes. And Haley, Tharani, and Susanna are all contributing authors to Astrobytes. And the Astrobytes daily summaries and live streams have been appearing both there and on AAS Nova. So today we have 4 presentations, all related to evolving stars and nebulae. And I'm especially excited about this briefing because one of the nebulae being discussed is one that I actually observed in my own PhD thesis. So the speakers will appear in the following order. Daniel Wang from the University of Massachusetts Amherst will speak on scientists explaining a jet pointing the wrong way. And then we're going to have 3 related presentations under the umbrella title, New Looks at Old Friends, Hubble Space Telescope and Radio Imaging of 2 Quintessential Planetary Nebulae. The first is the Butterfly, NGC 6302, which will be presented by Joel Kastner from the Rochester Institute of Technology. He'll be followed by Paula Moraga, also from RIT, so I guess I was wrong about people not being in the same state, and Jesse Bublitz from Green Bank Observatory. They'll be covering the Jewel Bug, or NGC 7027. And so let me just remind everybody that we are streaming live to YouTube, and we are also recording this session, so that if you have a problem being recorded, now would be a good time to bail, but I hope that doesn't apply to any of our panelists. All right, so with that, we're all going to mute and stop our video, except for our first speaker, Daniel.
Is that okay? Looks okay.
Yep, you're good to go.
Okay. Hello, everyone. Welcome to my talk. So I'm going to talk about some weird ejection of very high energy particles from a pulsar. We know the pulsars are the magnetized neutron stars, which born out from the massive stars at the end of their life, run out of the nuclear fuse and collapse. So because of a strong magnetic field and the rotation, the pulsars are energetic source, accelerate the particles to very high energies and produce the winds, called a pulsar wind. And so because it's a wind, you tend to produce, the pulsars will produce bubbles around them, as normally seen, for example, in the Crab Nebula is a good example. The Crab Nebula inside a supernova remnant. So the pulsar I'm going to talk about is this one called PSR B2224 plus 65, which is pretty normal, like kind of pulsar, very ordinary in terms of period, rotation period, and energy, and kind of intermediate age in terms of how fast it spins down and at a reasonable distance. One thing about this pulsar is, special about this pulsar is it moves very fast. Projected in sky, or the proper motion of the pulsar is about 900 kilometers per second. So this is definitely is moving in the interstellar medium outside the supernova remnant already, because it moves very fast. Then will be supersonic motion, and supersonic motion will produce a shock in front of this bubble of pulsar wing nebula. And because of this ram pressure or the wing of interstellar medium, you will see the bubble will be squeezed into a narrow features, so produces so-called Gedon nebula because of shape, as seen in here in the H alpha image of the system here. Pulsar is located right here. So actually the nebula has substructures. And again, even nearby, close to the pulsar, you see this Hubble image, which shows up another kind of small Gedon shape. Okay, so that is pulsar is right here. So you basically that's what you expect from the fluid dynamics. Everything will be kind of blow backward because it's material from the pulsar. And here H alpha traces the interaction between the pulsar material and the interstellar medium. But when you see the in X-ray, so you find the actual things are ejected in some sideways. That's kind of weird, because now if you drive the car very fast, you have to be blown backward. That's what you expect, as you've seen in the Gedon nebula here. But X-ray totally different. X-ray traces here, we believe, is very high energy particles, which like 100 TeV kind of particles, and produce so-called synchronous radiation. That's the particles moving in the magnetic field. And so for these very high energetic particles, they seem to be going sideways against the fluid dynamics we know. But this actually has been known for a while, okay? So this kind of the first such system being observed. At about 10 years ago, a student of mine and I actually used two channel observations to prove actually this jet-like features actually is moving together with the pulsar, in kind of synchronized fashion. It's clearly prove actually the physical association of the jet-like feature with the pulsar, which was initially has some doubt. Okay. Also, another thing, this feature is so straight. If you think about if things are moving fast, like a garden hose, if you have water coming out, if you move very fast, then the water should be bent, right? Because the wind. But here you see actually it's very straight. So this is another kind of weird characteristic of this feature. These are the two initial observations we used. So first epoch and second epoch, which is about 6 years apart. So each has exposure about 50 kilosecond. The second exposure has, because of have high background, so it looks noisy. But nevertheless, you see this linear feature here getting closer to this reference line in the sky. This indicates the whole feature is moving together with the pulsar. Pulsar, this is direction, the pulsar is moving. Now we have third epoch observations, but also 6 years later. And so this exposure is longer, 100 kilosecond. And so you compare the three epoch observations, you start to see the changes of the substructures. For example, this is a gap, which is only seen in the first epoch, not in the other two epochs. And also you see some local enhancements, which disappeared in somewhere, but you also see some other features in other epochs, but not in the first ones. So that indicates the structure is dynamic, changes with time. But also you start to see some other features here. This I initially called the counterjet on the other side, but also faint features which coincides with this Guitar Nebula shape close to the pulsar. Of course, now we have 3 epochs of data. We can stack them together. First, stack them in sky. Then you see the image of the pulsar is elongated because of proper motion at different epochs. Okay, and also you see the features which kind of blurred a little bit, and then you can stack also in the rest frame of the pulsar. For example, in the first epoch rest frame, then you see the pulsar is more point-like, and these features is a lot sharper than if you stack in the sky, because now you just move together. You stack in the rest frame of the pulsar. That again, that shows this actually proves definitively these 2 features here, are associated physically with the pulsar itself. So these are the features that I call jet, counterjet, and trail. And since then, a few other misaligned X-ray features have been discovered around other similar pulsars, kind of intermediate age, fast-moving pulsars. So that stimulated a lot of theoretical studies in recent years. I show a few examples here. So this is kind of an inner region. You see the pulsars have the magnetized, have different polar regions. So the particles will eject from the polar regions of the pulsars, which because open field producing the wing. The different regions that will produce, they have different combination of the positive charged positrons, which are antiparticles of electrons, and others will be negative charged electrons. So it's direction dependent. Now, these are the simulations, which is MHD simulations, and together with the particles from the pulsars from different parts of the directions from the pulsars. Now, depending on the relative angles of the spin axis, magnetic field axis, and the proper motion, and the interstellar magnetic field, they all have directions. Then in some region, for example, the magnetic field will be in the different directions, interstellar versus the magnetic field in the pulsar wing will be, so magnetic field can be cancel each other or annihilate, weakening the confinement of charged particles, because charged particles normally cannot easily cross the magnetic field. But that also confinement depends on the energy of the pulsar, the electrons or positrons. The higher the energy of the particles, the more difficult to confine, because it's called gyro radius, which become bigger and bigger with the energy. So for very high energy particles, as shown here, depending on different signs from different parts of the pulsars, will be able to escape. And this escaping of the high energy particles, depending on these relative angles, this is for one particular configurations, that proves actually you can, in some regions, kind of weakened magnetic field confinement, then the particles for particular kind of charge will be able to escape, produce kind of linear ejection of the energetic particles. On the larger scales, once you escape from these Bower-shocked confined regions, then the particles will tend to be diffuse or move around the large scale interstellar magnetic field, because the magnetic field is everywhere, kind of invisible hands which regulates the motion of the charged particles. But that is this picture, which is still not only qualitatively explains these kind of weird ejection of high energy particles from pulsars into interstellar space. And so there's certainly more work needs to be done. But this actually is very important, not only about the ejection itself, about the acceleration of particles, confinement of the particles, but also about the explanation of the excess of the positrons, which have been seen around in solar, actually in the Earth neighborhood, the cosmic rays. We know for a long time now there's a positron excess, which has been considered as kind of evidence for dark matter annihilation, for example. But the ejection from the nearby pulsar, like the one we are talking about here, might provide an alternative explanations for the excess of the positrons we observed near the Earth. Okay, so that is very much what I have talked about. Here's summary. So basically, we have observed kind of jet-like features from this pulsar, and they have the same proper motion because they move in same direction. So it clearly proves these features are physically associated with the pulsar. The main jet, for example, is about 62 degrees misaligned with the Gedang Nebula, which is backflow. Okay, is about a couple of light years long, quite a very large distance. Okay, it also shows substructural variations with time that still needs to be explained theoretically. And also we detected for first time the counterjet as well as the faint X-ray trail, which actually coincides with the nebula. But these features are much fainter than the main jet. That's kind of still something quantitatively needs to be explained. The magnetic field, but the bottom line is the magnetic field seems to play a central role in formation of the features. These are the features which representing the synchrotron radiations, basically the particles moving in the magnetic field. And so with very high, so these are very high energy particles leaked out from this power shock backflow. Okay, kind of going depending on the relative angles of the axis of rotation magnetic field of the pulsars and the interstellar magnetic field and the motion of the pulsar. And so therefore this pulsar actually provides a spectacular example or laboratory for studying extreme energetic particles and their dynamic interplay with the magnetic field from in the pulsar wind, and the interstellar medium, and may also similar phenomena in solar neighborhood could explain, for example, the excess of positrons observed in the Earth's neighborhood. So I stop here.
All right, I guess I'll jump right in then. Thank you, Dr. Wang. Can everybody see that okay?
We're not seeing your screen just yet.
Yeah, why is that? There, how about that?
Coming up now. Oh, you keep losing it.
Oh, geez, it's one of these things where when I go to the...
Okay, we're good now. This is it.
Okay.
Don't change anything.
Yep, all right, fine. Thanks, sorry for the little glitch. And thanks everyone for sticking with us here to the end of the meeting. I guess maybe the AAS has saved the best for last in Dr. Wang's bizarre misaligned jet. And then what my collaborators and I, and Rick, apparently, the AAS press officer, regard as some of the most beautiful objects in the sky, NGC 6302 and NGC 7027. So you see the people working on this, this program of HST, Hubble Space Telescope imaging using Wide Field Camera 3. You're going to be hearing talks in a second from Paula Moraga, who's a present PhD student working with me at RIT, and Jesse Bublitz, who's a recent former student at RIT, PhD student, who's just begun a postdoc at NRAO Green Bank Observatory. And you see other collaborators here, Bruce Balick, Rudy Montez, Adam Frank, Eric Blackman. I will be sort of serving triple duty here in the sense that I'd like to tell you quickly a little bit about background about Planetary Nebulae. and then a little bit about the program, and then a little bit about NGC 6302. First of all, planetary nebulae, as I'm sure many, if not everyone on this call, on this Zoom is aware, are not planets that are nebulae. That's a misnomer that goes back to the days of Herschel when these objects were first observed through telescopes, and they sort of resemble planets. No, instead, planetary nebulae are the ejected outer atmospheres of red giant stars that are now being ionized by radiation from the former core of the progenitor star, the star that became a red giant and is now disintegrating. That ultraviolet bright core is a future white dwarf. And so we're starting to see that white dwarf become unveiled. The transition from the spherical red giant to a highly aspherical planetary nebula, highly aspherical in many cases, it takes place over a few thousand years, which is an astronomical eye blink. And so astronomers are very interested in understanding the physical processes and mechanisms that explain this dramatic transformation from a spherical star to an extremely aspherical object, a nebula like this. The present theory, most would agree, not everyone in the planetary nebula field, that the varied shapes of planetary, well, I think everyone would agree about this first statement, that the varied shapes of planetary nebulae are due to the interaction between the new wind that's coming off of the white dwarf at present time and the former wind that was ejected by the red giant star. So the former outer layers of the red giant that didn't participate in nuclear fusion is now being blown away by the core that has inherited nuclear fusion products. So that's not too controversial. What is controversial is what's causing the change in shape. And by and large, over the last decade or so, it's generally agreed now that most of these objects are the products of binary stars. There's a binary companion to the mass-losing red giant star that has affected the way the mass has been lost. And so hopefully by studying these objects, we can start to understand some of the more exotic and important objects that people are studying right now in astrophysics, like merging neutron stars, for example, or merging white dwarfs that are going to generate gravitational waves. So the background for this particular program of Hubble Space Telescope imaging, well, as Hubble approached the end of its third decade of service, you can read here for yourselves, the potential of the Wide Field Camera 3 to obtain a fully comprehensive set of emission line images running all the way from the near ultraviolet to through the optical to the near infrared, which Wide Field Camera 3 can cover, had yet to be exploited for any individual planetary nebula. We were sort of shocked and amazed when we saw this. My jaw hit the floor, especially with these two objects that are so well studied and well regarded in the planetary nebula community for teaching us so much. Neither of these objects had been observed comprehensively by Wide Field Camera 3, and NGC 7027 hadn't been observed at all. These are some of the youngest. These are two of the youngest and most rapidly evolving planetary nebulae, we think. Both of them feature these very striking structures with juxtaposed point symmetric and bipolar structures and ring-like structures in the case of 7027, and Paula will talk more about that. And they also have large masses of molecular gas and dust, so they can teach us a lot about what happens to the cold material or cool material that came off of the red giant star as it's impinged on by this very high energy ultraviolet light. So this is kind of an eye chart, and I apologize for that, but it just gives you a flavor for the different sorts of things we could do with a program like this, using a variety of filters on Wide Field Camera 3, targeting a variety of emission lines. If you want to know more about that, I encourage you to go to this paper, which describes it in more detail, that appeared in Galaxies, in the Galaxies journal that my collaborators and I generated as part of a workshop on planetary nebulae. You can go there and read more about the program. So, okay, quickly, NGC 6302 is located about 3,600 light years away from Earth. It's in the general direction of the galactic center, but it's about 10 times closer than eight times closer than the galactic center to Earth. And it has one of the hottest central stars. It has one of the hottest stars known in the universe, 300,000 degrees Kelvin. Its main rival actually is probably NGC 7027 and a few other planetary nebulae. They're almost that hot. The nebula was ejected over about 2,000 years ago. Several studies have shown that the nebula was ejected about 2,000 years ago. And in addition to the brightly glowing gas that you see in this iconic wide field camera 3 image at the right, there's large masses of dust and molecular gas in this nebula. Now, as I mentioned, the nebula was imaged. It was one of the first light targets for wide field camera 3 back in 2009. And there was an apparent detection of the central star in those images, and actually a paper published analyzing that detection of the central star. I'll get back to that in a second. But first, just I want to sort of show you the range and the coverage that we were able to get with the wide field camera 3. These are the UVIS, or the ultraviolet invisible module images that we took. We got half a dozen, actually got one more that I'm not showing here is because the signal to noise isn't very good. But these 6 images span a wide range of so-called excitation states, ionization states of elements. You see here everything running from, if you can see my pointer, from neon 5 over here in the upper left corner to sulfur 2. And this means 4 times ionized neon. This means once ionized sulfur. And here we have hydrogen that we see recombining. So these are atoms of recombining hydrogen. So it's protons and electrons that are recombining and emitting light as they recombine in the nebula. So those are the ultraviolet invisible images. These are the infrared images, which run from a wavelength that's about twice what the eye can see out to a wavelength that's around 3 times what the eye can see, 1.1 to 1.7 microns or so. And I'll just point out to you, one of these images is not like the others. This is an image that was taken in the light of singly ionized iron. And that, it turns out, I'll show you a montage here of several images just to kind of make the point a little bit more obvious. But that iron that you see glowing here, rendered blue, is a tracer of very fast moving winds, where you have a very fast moving wind from this central star that's hitting slower moving material, as I mentioned before, that was ejected by the red giant. So that is really the smoking gun, almost literally, of the interacting winds scenario that people that the theorists have proposed shape these kinds of objects. And you see some other lovely features of this nebula too. We've started now working with the so-called line ratios that we can use. So you see in red the ratio of 2 hydrogen recombination lines that are showing us where dust is residing in the nebula. Paula will show another example of this in a minute for NGC 7027. But basically the ratio of those 2 lines should be constant. And if we see, that's the Paschen beta and H beta, that is, if we see variations, then we know that there's dust in the way. So we can see now exactly where the dust is in this nebula very clearly. We can see where the fast wind is hitting the slow wind. And the thing that's kind of dominating the view here is the green, that's nitrogen. There's a tremendous amount of nitrogen that's been released into the interstellar medium by this nebula. By the star that generated this nebula. And that nitrogen is something we're all breathing right now. So this is telling us exactly where this nitrogen is being generated in present generations of stars. One last thing, when I got this set of infrared images off the Space Telescope website after we'd taken the data, I was thrilled because I thought we detected the central star right here at the heart of the nebula and confirmed the previous detection of central star, but we're now seeing it much more directly in the near infrared. Well, wrong. The central star was here in 2009. It was here in 2019. That's not the central star. That's a foreground field star. And in fact, our working hypothesis right now is that this is where the actual position of the central star is, midway between these shell-like features that you see that we're seeing in this difference image. It's the 2019 image minus the 2009 image. So we can see the differences in the nebula itself in those 2 images. We can see the expansion of the nebula itself. We can see that this is just a star that happens to be moving through the line of sight right now toward that nebula. It's just bad luck that at this particular point in the universe's history, it just happens to be sitting smack dab in the middle of this nebula. It's just a bystander. So I'll leave you with that, and I'm going to overlay here our new image of NGC 6302 that we're generating from the line ratios we have over Judy Schmidt's beautiful multicolor overlay that appeared as an APOD last summer, an astronomy picture of the day. And now I will shut up and turn things over to Paula.
Thank you, Joel. All right. So my name is Paula Moraga. I'm a PhD student from Rochester Institute of Technology, and I'm going to talk a bit about the analysis that we've been doing with NGC 7027. So NGC 7027 is a young, rapidly evolving planetary nebula. It has a very unique structure. So it has this ellipse that we see here, also this belt, and all of these jets that are coming out. It's got the rings or spirals that are occurring around it. A very hot central star of almost 200,000 degrees Kelvin, and then just large amounts of dust and molecular gas, which we'll learn about later on. So here are some line ratio images. So we took some of the emission line images that Joel had talked about and are just comparing them to each other to see what they tell us about the nebula. So on the left, we see H alpha over H beta, which are two recombination lines, just as he had mentioned. And what these lines tell us, since they're at different energy levels, is where there's extinction in the nebula or where there is dust. So this is kind of like the dust exoskeleton of NGC 7027. And then here on the right, we have oxygen 3 over H beta, or doubly ionized oxygen. And what this image is telling us is where there's photoionization that is occurring within NGC 7027. So where the radiation of the central star itself is heating up this dust and causing for these ionization levels to occur. Then here on the left again, we have iron 2, a very clear picture of where iron 2 is occurring within NGC 7027. And what iron 2 tells us is where there are shocks that are occurring. So these are actual collisions that are happening, which are allowing for these ionization states to occur. And these shocks are what drive the shaping of planetary nebulae. And then on the right, we have sulfur 2 over H alpha, or singly ionized sulfur. And what this image is telling us is kind of both stories. So both photoionization and shocks are occurring, could be occurring at the same time, either or. So we can't really conclusively say, but nevertheless, it's still a really interesting image to look at. It's my personal favorite. It's just really nice to see how there's that symmetry that is occurring once again with the two jets that are opposing each other that seem the brightest. So this is an image that was put together with 3 of the line ratio images that I showed previously. So in the red, we have the extinction map that I showed. In the blue, we have the iron 2. And in the green, we have the sulfur 2. So it's just really nice to be able to see all of these together to see what they tell us about the nebula. And then also to see how the iron 2 is actually nestling in really nicely with the sulfur 2 there. So we've also been trying to measure the expansion of this nebula, although this is still kind of a work in progress, so we don't have anything conclusive to say about this today. And the reason why is actually because the way that you measure expansion within planetary nebulas is by taking an old image and a new image to compare to each other. And so what you want is for both of these images to be from the same camera. But unfortunately, we have these images, but from 2 separate cameras. So these are the images that you see here. They're both from the same filter, but they're using 2 different cameras from HST. The one at the top is from 2009, and the one at the bottom is 2019. And despite them being different cameras, you can still see, though, how much it is expanding just by eye, which is really amazing to see. And then also, we have been doing work to measure the extinction of the central star. So just measuring just how much dust is between us and that central star. And the way that I was able to do this was by measuring the flux at 9 different wavelengths. So those are those purple stars that you see there on this plot. And that dashed line is a model atmosphere for a white dwarf of 200,000 degrees Kelvin. And so that's what we believe the central star to be. And so Using an extinction model that is well known by Cardelli et al., I was able to write a function to correct for this extinction so that these plot points follow the model nicely. So that's what we want to see. And in turn, we were able to find the extinction of the central star to be about 2.57 magnitudes. So that is all for my portion, and I'm going to pass it on to Jessie.
All right, great. Thank you very much, Paula. All right, let me get set up here. Okay, so I will be continuing on the shoulders of my colleagues and talking a lot more about NGC 7027, this time using radio observations to try and characterize the shaping of the nebula. So NGC 7027, as Paula stated, is a young and rapidly evolving planetary nebula with an extremely hot and bright central star that's providing a source of ultraviolet and actually also X-ray radiation. And it's for this reason that we chose NGC 7027 as a means of testing how this high energy radiation is shaping and affecting the structure that we observe. So to do this, we've utilized the Northern Extended Millimeter Array, or NOEMA interferometer, which is up in the French Alps, in order to observe at roughly 1 and 3 millimeter wavelengths the molecular ions CO+ and HCO+. Now, these are two excellent irradiation tracers that are highly abundant in NGC 7027. And by exploring them, we hope to understand how they might be shaped by ultraviolet or X-rays, respectively. Now, the interferometer here is much like one that you've heard of recently to observe the black hole at the center of the M87 galaxy, which used a series of radio telescopes around the globe. NOEMA, on the other hand, is much more compact, just on the top of a mountain, because we don't necessarily need the same extreme scales of resolution for a very distant black hole. And what we were able to produce is the first CO+ image ever in a planetary nebula, and in fact, only the second image of CO+ in any astronomical object. Now, CO+ is an excellent reactive ion, which has several different chemical processes, primarily two scenarios here in planetary nebulae, driven by ultraviolet or by X-ray radiation. So, in order to try and understand what is shaping this nebula, we've compared it with archival molecular hydrogen taken from the Hubble archives. And already you can start to see some similarities in the structure. Now, molecular hydrogen is an excellent tracer of UV irradiation. So it's a great standard from which we can compare our observations. Now, in addition to CO+, we also observed HCO+, which can also be formed by UV interactions with CO+. Thus, we would expect that the two to be co-spatial if they are formed through UV processes. So what I've done is taken the molecular hydrogen on the left and HCO+ on the right and produced contour lines representing their shapes and overlaid them onto a CO+ map in order to just compare how they, where they exist within the nebula itself. And the results speak for themselves. On the left, you can see that those molecular hydrogen contours lie beautifully above the CO+ image. Not only do you have that very common four-leafed clover structure of NGC 7027 present, but also You see those two bright points along the waist of the nebula, which line up very well as the representative torus of gas, or that belt, as Paula described it. This suggests that CO plus is indeed, much like molecular hydrogen, a UV tracer. Now, moving to the right, we can see that the HCO plus image is quite a bit different in structure. While it does generally outline the molecular gas, it's much more offset and further out from that central star. In fact, if we compare those two bright peaks at the waist, from CO plus to HCO plus, we actually compute an offset, an expansion of 1 arc second, or about 900 AU. So that's 900 times the distance from the Earth to the Sun that HCO plus peaks. In addition, you can identify these significant outflows to the north and south, where the gas extends further out. And there seems to be a significant lack of HCO plus emission in that lower left-hand quadrant there. So all of this put together suggests that HCO plus is not co-spatial with CO plus, and therefore is likely not produced by ultraviolet radiation, but rather through X-rays. So already we have two molecules that are beautifully representing two different processes within the planetary nebulae that can help us understand how it's being shaped, how this high energy radiation coming out from that central star region is driving what we're seeing. But we can go in a step further by looking specifically at the velocities of that HCO plus emission. So on the right, we have a figure representing the total intensity, or the emission of light observed in HCO plus, moving from velocities that are moving towards us on the left out to velocities moving away from us. And that red dashed line represents the overall velocity of the planetary nebula with respect to us. So on the left, we have peak emission that's highlighted in blue, which represents blue shifted gas towards us. And on the left, we have symmetrically opposite component of red shifted gas. Now, when you plot the contours of those velocities onto this infrared image, which was described earlier, you can see that these HCO plus clumps are lining up beautifully well with those previously observed outflows, or ends of a pillowcase, effectively. And more than that, you can see that for every blue shifted component on one side of the nebula, you actually see red shifted on the opposite side. So what we're observing here, if we take a side view, is actually the nebula itself is being shaped and torn through by these jets of fast moving gas, which is producing the HCO plus emission through formation of X-rays. And we're actually able to determine its structure, its orientation with respect to us, due to this blue shifting and red shifting. So we can slowly piece together all of these different jets that are observed in the gas. In this case, the red shifting component actually seems to be entirely absent, likely either due to extinction from overlaying dust, or that the shock process is strong enough to completely dissociate any HCO plus formed. And lastly, we actually have this, what appears to be inverted jet, that if you look at it from a side view, actually appears to be moving almost along that waist. So altogether, we have evidence for these periodic jets that are tearing through the otherwise fairly spherical or symmetric envelope of the planetary nebula NGC 7027, indicating that it has been going through very interesting processes in its still short lifetime that are making such vast ripples in these jets of material. So I'll leave you all with several of the images that my colleagues have been showing off of NGC 7027 and NGC 6302. And I thank you very much.
Terrific. Thank you all. Very interesting set of presentations. Lots of interesting results to talk about. Haley Wall is going to read the questions aloud. Remember, if you have any questions, please put them in the Q&A box. And also, if you see a question that you are particularly interested in seeing answered, you can upvote it by clicking on the thumbs up icon. So I'll turn it over to you, Haley.
Thanks, Rick. And thanks to all the speakers for their interesting talks. First, we have a couple of questions from Jan Hattenbach, who is freelance. The first one is for Daniel. Is it expected that the interstellar field lines seem almost perfectly straight over the length of the jet, more or less 2 light years?
Yeah, that's a good question, actually. I don't think we know very much about the magnetic field overall structure in a typical interstellar medium. We do know in special cases, for them, molecular clouds, where you easy to measure the polarization, and we do know how the magnetic field organized, and also outflows, for example, M82. And you see the magnetic field can be coherent on even kiloparsec scales. So in principle, there's no issue with the coherence of magnetic field on the few light year scales, but we don't know really about the typical interstellar medium this pulsar is moving through.
Great, thanks. The next one is again from Jan Hattenbach to Joel or Paula. Joel mentioned that the PN shapes may betray the presence of binary companion to the PN progenitor star. What happens when what happens to these companions once the nebula has formed? Are they still orbiting the hot remnant star? And have any of them been found?
Paula, if you like, I can take this.
Yeah, that's fine.
Okay, so yeah, that's a great question. And in fact, up until about 10 years ago, I would have said we really have no idea. We would suspect on theoretical basis that the binary companion can survive, but it's been very, very hard to find binary companions to the central stars of planetary nebulae because they're so luminous. They've just been red giants. They're sometimes 10,000 times more luminous than the sun. So trying to find a main sequence of normal star next to that incredibly bright dying star is next to impossible. But many of our colleagues now have had great success in detecting binary companions around planetary nebula central stars. They do seem to survive. And in fact, we know that because there are short period binary stars in which there's a white dwarf in a binary system with a main sequence star, and in a very short period. And the only way that could have happened is if this poor main sequence star suffered through the mass losing star going through this process of becoming a planetary nebula and actually came out the other end as a main sequence star. Now there are some cases, I don't want to go too long here, but there's some cases where if the star is low enough mass, say a brown dwarf or something like that, it could be, or a planet, it could be shredded. And that's another possibility. But probably by and large, these things are surviving, which is really interesting.
Great, thank you. The next one is again from Jan for Jesse. Could you tell us a little bit more about these interesting processes that cause the various jets?
Right. So the jets themselves are this fast-moving outflow that is directed from the central star itself and interacting with the slower-moving envelope, as Joel had described earlier, from an earlier part of the star's emission. Now, the jets themselves, the formation of them is a bit more nuanced, but one possible formation of them is through interactions with a binary companion, in which accretion is then caused to rapidly shoot out from the poles of the central star itself and providing these great outflows that we observe. So
Uh-oh, it looks like we've had a bandwidth hang up or something for poor Jesse. Hopefully he'll come back to us shortly.
Yeah, I could finish the sentence. I think I knew where he was going.
Go ahead.
You have a student for a few years, and you understand how they're thinking. So I think just to finish Jesse's thought there, there's kind of two different scenarios where you get these jets, and I think Jesse mentioned one of them, which is you can accrete material onto the binary companion. The binary companion can launch jets, or the binary companion can plunge into the star itself, accrete into the star, and that can send material flying. I tend to prefer the latter scenario for NGC 7027 because Jesse showed very convincingly the jets are going off in all different directions. It's absolutely crazy and chaotic what's happening in that star in that nebula right now. In the case of 6302, there's more collimation, more sort of directed flows that would suggest that maybe we're seeing a companion star that's ejecting the material.
Great, thank you. We have another question that has just come in from Jennifer Wiseman from NASA. Beautiful images, nice work. For Paula, what will be what will you be next studying about NGC 7027? What are the unanswered questions ahead?
Well, we still have to finish studying the expansion rate of NGC 7027. So that's definitely something that I'm going to be trying to look at next. But then also looking into what the mass or the radius of the central star would be. And so I kind of made some headwork with that by finding the extinction of the central star, and using that model, I can find the luminosity and then keep working on that and try to figure that out.
Great, thanks. And the next part is for Jesse, who has just joined us again. Okay. For Jess. Sorry, go ahead.
Yeah, you'll have to read him the question because he didn't hear it.
Yeah, sorry, I missed what's been going on. One of the downsides of living in rural West Virginia in the National Radio Quiet Zone.
Yep. So the next part for Jesse from Jennifer Wiseman from NASA. Have you compared your data with actual X-ray observations?
Yes, well, so we have done some preliminary comparison, but nothing detailed. And actually the past Chandra observations, I don't have any good graphics to show off, but in that northwestern quadrant where you see not a lot of extinction gas from Paula's H beta over H alpha image is where you see a lot of this X-ray emission poking out. So that coincides really well with the initial jet that I showed you, which doesn't seem to have a red shifted component, just a blue shifted. So that seems to be the most recent and currently active jet. And that's why we're actually able to observe the X-rays coinciding with it, just being, the gas there has just been blasted away. And I'm not sure how much of the previous question I was asked you guys all heard. I don't know if you would like me to try and go back with that.
I tried to jump in and put words in your mouth. I think I finished the thought for you, Jesse.
All right, well, if there's more questions about that, we can always chat afterwards.
Yeah, luckily we noticed that you froze pretty quickly.
Thank you. You
definitely went radio quiet. I don't see any more questions in the Q&A box at the moment, but I have a question for Daniel. This relates to your discussion about the jet being so very straight despite having the same proper motion as the pulsar. I don't believe you addressed this, but does this mean that the jet is extremely young and that it's extremely relativistic? In other words, that that it hasn't it hasn't had time, hasn't really had time to bend yet because it's just been formed so very recently? Or is there some other mechanism that's, I mean, the magnetic field, sure, but it just seems odd that it would be so straight for so long.
Yeah, so that's actually, yeah, I didn't really fully address the question. Actually, jet, actually, you should expect some ram pressure, which bends the jet. But actually, this is the probably what I should not call the jet. So it looks like a jet, but actually it's a kind of diffusion of the particles around the magnetic field. The shape of the linear shape is due to the magnetic field structure. So basically, when the pulsar moves, it continues illuminate magnetic field at different on the way. So this is, but this issues why so much long, why we don't see, for example, the cooling of the particles. There's still quite some issues. Basically, you have to very fast, but have to stop somewhere. Nobody knows. The people now already kind of theory is focused on the escaping of the particles. But in terms of how the particles propagate around the magnetic field, whether you have a continued acceleration of particles, these are issues that still need to be solved.
Okay, thanks.
Okay, we have another question from Jennifer Wiseman for Joel. Are you going to take fresh looks at other planetary nebulae?
Hi, Jennifer. You bet. Yeah, as I say, we were sort of floored when we realized that the Hubble's Wide Field Camera 3 had not been used in this way for the well-studied planetary nebulae. We observed, I forget how many, it was something like 50 nearby planetary nebulae as part of the Chandra X-ray Planetary Nebula Survey. And we learned an awful lot from that survey. So if I had my way, I would observe another 48 or so planetary nebulae exactly in the same method, just covering every emission line we can easily cover with Wide Field Camera 3 that will tell us something about extinction, excitation, shocks. Try to cover them uniformly this way. And a little footnote, it's probably not fair, but anyone on the James Webb Space Telescope time assignment committee, there's a, well, anyway, I won't say more. Okay, I'll stop right there.
All right, it looks like we've exhausted the questions and we're coming up on the end of our hour. If anybody does have a last question, fire away quickly because we're going to wind it down otherwise. So again, I'd like to thank all of our speakers for being willing to participate and share your exciting science and images with us today. I want to thank the audience, all of you who've joined us, not just today, but over the course of the week. It's been very exciting, and it's been a while since we've ever tried to cram 10 press conferences into one meeting, but having the extra day certainly helped. Now, there is a press release out from RIT, and there's another one coming from UMass. We haven't seen it appear online yet, but it should be up anytime now. So I want to thank the public information officers at RIT and at UMass for for pulling those press releases together, and also for the help that they and the folks at the Chandra X-ray Center gave you in preparing for these briefings. There's someone else I want to thank, which aside from my team, which I introduced at the beginning, I want to thank the second logo that you see on our virtual background, USRA, that's the Universities Space Research Association. They have very generously been sponsoring the press facilities at our AAS meetings, and they were prepared to provide coffee and snacks, mid-afternoon cookies, and so on for this meeting. Instead, they contributed to the cost of our infrastructure. But I want to thank Soraya Faruqi and her team at USRA for their generosity in sponsoring us and in doing everything they can to make the experience as pleasant as possible for the beleaguered journalists who have to file on deadline and spend long hours in the press office. So thanks again to USRA. Now it's my, I'm sorry, there's one question left and it's not quite 5:30 yet. So I'm going to let Haley address that question, and then I will finish up. Oh, that was just nice job speakers.
Well,
Okay, great. It's from
Yeah.
Jennifer. Yeah, she's just saying, nice job. Great. Thank you, Jennifer. Appreciate it. Okay, so I always traditionally like to end the final briefing by announcing the date and time of the next one. So I'm going to very briefly share my screen now and announce that the next briefing will be on Monday morning, June 7th. Now, we think that it will be in Anchorage, but we don't know for sure yet because everything depends on how quickly the Biden administration is able to recover from the situation that they've been left with the vaccine distribution. If we can get enough vaccine distributed early enough in 2021, we should be able to announce that the meeting will take place in Anchorage, Alaska as planned. If that doesn't happen, we'll inevitably have to go virtual, but that decision hasn't been made yet and probably won't be made till March, I would say. But in any case, we can confidently predict that there will be a press conference on Monday morning, June 7th. If not in Anchorage, then right here on the interwebs. All right, so that's it for me for this time. And I want to thank everybody again for coming. And we'll wrap it up. And I hope to see some of you this evening at my, I guess it's a celebration.
It is.
I'm looking forward to it. And Susanna should know because she's the chief co-conspirator. All right.
I will
Thanks,
drop the
everybody.
link one more time back in the Slack.
Okay. Thanks a lot. Take care, everybody.
Thank you,
We
Rick.
appreciate it. You bet.
Thanks, Rick.